Okay, the final part is about small angle approximations. If you take a look at what you have there on the board, you have y equals x, and you have y equals sine of x, where the x, where sine of x is in radians, so if x is in radians, if you like. And can you see that for small values, the red line pretty much tells you the value of the blue line. So that could be important if you didn't have a way of finding out sine. In other words, sine of x is about x for small values close to 0. That's the same graph in degrees for sine of x. And you can see it really doesn't work here. It's not the case. We don't have to prove this anything right now, but we do need to know that what this means is it means when we use radians, small values for sine of x and cos of x and so on, and tan of x, okay, we have a way of doing this. And this explains how we can prove different results later on and why we're able to do lots of useful things. So in a nutshell, we need radians. We need to use them. These three are in your formula booklet, but you need to know these. So for small angles, and you need to watch out for phrases like for very small angles, for angles close to 0, okay, something like this. Sine of theta is pretty close to theta. Tan of theta is pretty close to theta. Cos, you need to be a bit more careful for this, okay? And just like in chapter 4, when you had 1 plus x to the, what was this? This was typically, what was this here? N? I think this was n. You might remember you had like a formula in the formula booklet for chapter 4 for binomial, and the thing that was in the x position, sometimes it wasn't x. So your x was sort of like 2x and so on, and you had to be really careful with substitution. Something very similar happens here. So for these, the thing that is in the position of theta goes in the position of theta here. So when we read this one, it's quite useful to put brackets here to avoid a mistake. You'll see what I mean in just a moment. So when theta is small, find the approximate value. Well, for sine of 2 theta, okay, it's approximately whatever that theta is. So sine of thing is approximately thing. So I'm going to say that's 2 theta. Tan of thing, tan of other thing is about the same as thing. Are you with me so far? Over 2 theta is just 2 theta. So look, that's 3 theta over 2 theta. So the answer's about 3 halves. For B, let's have a go. Cos of thing is equal to 1 minus thing squared. 1 minus thing squared must be like this. Must be. I'm stressing this because this is such a common mistake. You do not need to make this mistake. Substitute the thing that's in the position of theta for the thing that's in the position of theta, please. Over 2. This is how it must be. Cos causes lots and lots of mistakes with this. Let's clean this up. So this is 1 minus 16. Yes, 16. Distribute the power. 16 theta squared over 2, which is the same as 1 minus 8 theta squared. Okay. That's all just this part here. Now, take away 1, cancel. And in the denominator, theta, 2 theta is, that's about 2 theta. So all in all, I get minus 8 theta squared over 2 theta squared minus 4 seems to be approximately what it's equal to. If you can do that question, you can more or less do this topic, okay? Pause the video, have a quick go at both of those there, and notice that the cos 2 theta is in bold for reasons that we just talked about. Okay, so 5 theta, 2 theta. Look at how 2 theta is in there, and it will become, this part here, will become 4 theta squared, which is then divided by 2, okay, which is where the 2 theta squared comes from. Hence, state the approximate value of this whole thing here. So this becomes this. Hence, state the approximate value. Well, this is all the same as this. So what happens to this for small values of theta? Well, imagine if they were zeros. Gone, gone, constant. Hence why they're called constants. -1 is the answer. Here are some previous examples, such as that from 2018. Okay, so 1 minus, let's use the result, put it in brackets to be on the safe side for this one here. So 1 minus 4 theta all squared over 2 theta to the 2 theta squared. In fact, I think we just did that one, did we not? No, we did not. It just looks very, very similar. Okay, so 1 minus 1, that would disappear. 1 minus minus, so 16. So I'm thinking 8 theta squared over 2 theta squared, which is going to become 4. You need more working out than that, okay? You need more working out, but I'm just doing that because we've just seen a very, very similar question. The your turn. Let's have a look at the your turn. So we know exactly what this result is because we've just got it. So why don't we copy that part down? So 1 minus 4 theta squared over 2 minus 1. Sine of 2 theta is about 2 theta. Okay. What we're going to get? We're going to get -8. Again, you do more working out, but you have more space than me here. Okay. You're going to get -8 theta squared over 2 theta. Cancel those, cancel those. I get -4 theta as a final answer. And that's actually, that takes you up to the exercise. Please do all of the exercise here because it's quite hard to find questions to complete about this. So I will just sort of leave with one final thought, that is, this is how it has appeared in a paper in the past. So it's appeared graphically. So let's just take you through. This shows cos of x, where cos of x is measured in radians. Starts at 1, down to -1, and so on and so on. Use the diagram to explain why. Well, the answer to this question here. So I don't know what cos of x minus 2x minus a half looks like. I don't know what that looks like. It says use to explain why this has only one real root. But we don't need to draw this. So a clever thing we can do about roots is we can get roots by breaking things up into two separate graphs that are easier to draw and then finding their intersections. It works as well. You might remember that from quadratics at the start of year 12. So if I had cos of x and I moved the 2x and the half to the other side, solving this is the same as solving this. Well, cos of x is already drawn. Use the diagram, not optional, use the diagram. Now draw 2x plus a half. So 2x plus a half is here. 2x is a steepish gradient that goes something like this. Why there is only one real root? Well, look, there's clearly only one solution from the simultaneous equation here. So that's why this thing that I'm not going to draw, and I'm not expected to be able to draw, has one root. Okay. There are some other clues here, so it's always good to make connections. 1, 2, 3, 4, 5, 6 and a bit. Do you know anything that's 6 and a bit? Yes, it's 2 pi. Okay. Given that the root of the equation of alpha is small, use small angle approximation. So could we use small angle approximation here? Well, yes, of course we could. For cos of x, that's a nice one. That's going to be 1 minus theta squared over 2 for that part. Minus, well, x is like the theta now, minus 2 theta minus a half equals 0. Okay, so you could solve this quadratic here, couldn't you? And that's the final part of how you do that question. So this is more sort of an application question. It's quite hard. It was very badly answered, this question, but it was badly answered because people didn't really understand what they were looking at and what they were meant to do. This idea, you will see this come up again over the next few chapters, but it was about graphically understanding what small angle approximation actually looks like. Okay, and that is the end of the chapter. So, like I said, lots of practice for this because you have quite a bit of trick coming up, so you need strong foundations for that. Best of luck.